Refrigerant 134A flows steadily through a 28 centimeter diameter pipe. It enters the pipe at 200 kilopascal and 20 degrees C with a speed of 5 meters per second. Heat is added to the refrigerant as it flows through the pipe, and it leaves the pipe at 180 kilopascal and 40 degrees Celsius. Find the volumetric flow rate at the pipe inlet, the mass flow rate, and the velocity and volumetric flow rate at the exit. This problem is intended to demonstrate the principle of conservation of mass. So in this particular problem, we have refrigerant 134A that's flowing through a pipe. We know the diameter of the pipe, so we begin with our usual illustration. So let's just say that this is our piece of pipe, and let's identify points 1 and points 2 as the inlet and exit from this particular pipe. We're given the diameter. So we'll just note that the diameter is 28 centimeters, and it's the same at the inlet and at the exit. We're given that it's refrigerant 134A, so let's just indicate refrigerant 134A. And we're also given some properties at both the inlet and at the exit, so let's just note that the pressure at the inlet, P1, is 200 kilopascals. We're also given the temperature at the inlet of 20 degrees Celsius, as well as the velocity of 5 meters per second. At the exit, we have similar information. We are given that there's heat added to the pipe, but this is not a first law problem. This is just a conservation of mass problem, so that's not something that's important. But we will indicate the given exit pressure and temperature as 180 kilopascals and 40 degrees Celsius. Now what we're trying to find in this particular problem is the volumetric flow rate at the inlet. So V1 is an unknown. We're also looking for the mass flow rate. And of course the mass flow rate is the same at the inlet and the exit. And after all, these are steady flow problems. And then we also are trying to find the velocity and the volumetric flow rate at the exit. So in other words, V2 is unknown, and the volumetric flow rate at 2 is also unknown. Now, let's keep in mind that in order to find the mass flow rate, we really need to know a little more than the area, the velocity, and the specific volume. After all, mass flow rate equals velocity times area over specific volume. Now, we know the velocity at the inlet. We can calculate the area based on the diameter, and we have the state at the inlet because we know two independent intensive properties, that is pressure and temperature. So we could easily go into our tables for the refrigerant, A11, 12, and 13, and find the specific volume. So let's find the mass flow rate based on the inlet conditions. So V1, A1, and specific volume V1. So that's something we can easily solve for. Additionally, to find the volumetric flow rate, let's just keep in mind that volumetric flow rate, V dot, is equal to the mass flow rate, M dot, times the specific volume. So once we have the mass flow rate, we should be able to find the volumetric flow rate. In fact, this is the same equation we're going to use at both points 1 and at points 2. Once we found the volumetric flow rate at point 2, we'll use the same mass flow rate equation as we did previously, although of course this time at point 2, in order to find the velocity. So we need V dot 1 as M dot specific volume V1. We also will note that V dot 2 is M dot times specific volume V2. And then lastly, we'll use the same mass flow rate equation, M dot, applied at point 2, so velocity times area divided by specific volume at point 2. So the problem is really pretty straightforward. Let's now go into our property tables and find the data we need. So at P1 and T1, at these two thermodynamic properties, that is at this state, this is a superheated vapor, so that means we're going to go into table A13. And the only property we need is a specific volume. We look at V1 as 0.1142 cubic meters per kilogram. Additionally, we're going to need information at point 2. Again, all we need is a specific volume. We'll go into exactly the same table. A13. And we'll look up V2. So as usual, we go into the pressure subtable. We read down to the 40 degrees Celsius line, and we find 0.1374 cubic meters per kilogram as a specific volume. We're also going to need to remember that area is simply pi over 4 times the diameter squared. So this is something we're going to use in the above equations. So now let's go ahead and solve this problem. With the given thermodynamic property data, we'll begin with the mass flow rate. So mass flow rate is the velocity, which is given as 5 meters per second, multiplied by the area. So pi over 4 times the diameter squared. We're going to convert 28 centimeters into 0.28 meters, so the units work out properly. We divide this by the specific volume, so 0.1142 cubic meters per kilogram. We see that everything cancels out except kilogram per second units, so we get 2.696 kilograms per second. So there's our mass flow rate. Now we'll move on to the volumetric flow rate equation. So V dot 1 is equal to the mass flow rate times specific volume. So it's just this equation above. So we have 2.696 kilograms per second multiplied by the same specific volume, 0.1142 meters cubed per kilogram. And we go through the math and we get 0.3079 cubic meters per second. Next, we're going to continue. Let's find the volumetric flow rate at point 2 now. So V dot 2, using the same equation as we just saw above, mass flow rate times specific volume. So we get 2.696 kilograms per second multiplied by 0.1374 cubic meters per kilogram. And this gives us a volumetric flow rate at the exit, 0.3705 cubic meters per second. And lastly, in order to find the velocity, we're going to use the same equation for mass flow rate as we did above. So we have mass flow rate, which we already found is 2.696 kilograms per second. And again, the mass flow rate is going to equal the velocity times the area over the specific volume. The velocity is unknown. The area is the same, pi over 4 times 0.28 meters squared, and then divide that by 0.1374 meters cubed per kilogram. We go through the mathematics here, and we end up with a solution for the velocity, and the velocity at 2 is just 6.02 meters per second.